So let's start our lecture 8. So this actually is the most general metric. Professor actually Sushant just told us this actually with the Fourier symmetry. This you can also deduce from the most general one I just derived with TR independent. Right? There are two functions. So here actually we consider this case. Like what I said, you can actually consider the same even for any edge, as long as f equal 0. Let's say here's r equal Rn. Now h should also have something like edge head. Here you have 0, let's say R1, R minus R2, R minus R1. As long as they have the same roots, this measure will apply. So this is only one we done. R1, R2 is F equals 0. Sorry, let me see. Where F equal, let's see, R minus R1, R minus R2, R minus Rn, F, R height. Okay?
So, R1, R2, R3 position of the horizon.
This is actually called the horizon. The largest one is called the Yuan horizon. But each of them is called horizon. So the most, this one, okay, good. This is actually R. So we have, let's see, R1, R2, Rn. This one is called Yuan horizon. All the rest is called Yin horizon. Okay, this is the Yuan horizon. So there are possibility, different theory you will see, even in Einstein theory, if we have a matter, this could be possible. Okay, so we consider all in the case H point called simple singular point. Okay, so then you can see even for the general case, this also you can apply, but this we need to have H at R minus R1, R minus R, which means the singular property should be the same in this one. As long as even H is different from 1 or F, if they have this structure, you can use the measure to generate the case. Okay? The only difference you will see, this is a function I'm going to introduce a G function. Okay? So if you really understand the part after this class, you should be able to do this easily. What we do actually is the following. The strategy is the following. Now, you see, if we have some singularities, we are either here or either here, right? You cannot have really in between. So, critical extension, the main idea is I just try to put these two regions together. Then, like papers, I glue them together, this part, then glue another part. So, the idea is very simple. If you, then let's say I first glue this part together, after that I glue this part together, then finally I get a whole piece. So we just do one by one, then you just put them together. So if it's one by one, then you will know, okay, we already did Schwarzschild case, then something will be similar. So exactly. So I'm going to first give the general ideas, then we can apply, come back to Einstein, Schwarzschild case, you say, oh, that's simple. But later you can consider it as a charter case. Charter case, like what I said, we have two horizons. Even for example, if I have a cosmology constant, I can have also two horizons, right? So that's in principle, you can work out all the details. Any question about this? Okay. So, Now, the first thing we want to like to see, okay, we have actually this is my TR is not F anymore. This is R. I want to see one observer start with, let's say, R equal 0. This is actually the trajectory of this observer, right? So, you know, this velocity of this observer will be U mu equal F minus 1/2 delta mu t. This is a timeline. This is not necessary. This is actually listener observes. This actually observes just sit on R equal constant, then moving with the time, structure of time. Okay? So then we actually introduce a quantity called acceleration, and mu, u, mu, nu. The summing could always actually is a current word. Right? So this is actually u, nu. So you will see this word equal, I call kappa alpha delta mu r. There's only the acceleration, there's only one component. Use the purpose. This is the current word. U, mu, nu, similarly equal. Similar. So where kappa equal R equal 1/2 F R prime. So this actually, this is the full velocity. This is the acceleration of this person. So this actually observes sit down with R equal constant there. Then we have R. This is called surface gravity. So surface gravity here is very important. Surface gravity means actually if you can say R equal constant surface, right? So what's the surface gravity? Exact corresponding to the acceleration. The acceleration. So this guy is phenomenal. If you have a black hole here, of course this will feel some forces. This actually fixed R. This is exactly the surface, like what we are sitting here. Our Earth actually is like a ball. We are on the surface, so our weight you can consider surface gravity, right? This is the same thing. So we are here. So this actually equal. This part. This actually is derivative. I have this one. Now, of course, if I consider this actually under the horizon R equal Ri, so this actually is the surface gravity of the horizon R equal Ri. So this actually we have this. So now, once I have this, I come back here, I will still use this actual relations. This will equal F R dt squared minus H R F R dr squared minus R. So I define my dr star or r star equal H R F R dr. This is, let's say, this equation is 1, this is 2, this is my preparation. I call this equation 8. So later I will erase here, that you can find from my lecture notes. So what I'm going to actually assume the following. I will focus only on one of the horizon. Let's see R8. Now I assume my R equal R minus RA over GR. So where GRA different from the 0, right? If it equals 0, then you have some. So you see here, can do the following. Once I do this, actually, I'm going to expand GR equal sigma I equal 0. Let's say I equals 0 to infinity, A and R minus R I. Well, A0 is different from 0. Why? Because of this one, right? R equal Ri, so A0 term is different from A0. This is an assumption. And this actually I equal di dr, right? So this actually I equal R. So I want to see you can plot here. Now again, for general case, you just simply you need to simply put H R equal R minus R A H A. Right? H A R I different from 0. Then redefine something G. So the same thing, so I just want to let you know, this actually can be generalized to the most general case. So once I have this one, you can see what's happening. I'm going to actually put it here. Now I will use substitute here. Okay. So this actually then R star will equal sigma n equals 0 infinity A and R minus R A and R minus R A dr, right? You see here, if I equals 0, I have N0 R minus I, so give me log, right? So this actually will give me the following A0 log R minus R A. Plus sigma A equal 1 infinity A and R minus R A. For R Ghosh. So I just consider Ghosh, you can actually usually consider a less than case, R case. So here is plus this. Now you can say A0 equal GR, right? The definition, R equal I, G0, because the higher the Y equal 1 is actually R minus R equals 0. So this actually also equal 1 F R. This exactly cover or cover A equal cover R. Separate derivative, right? You see now why I introduced separate derivative? So here, the important. I connect this one. Why? Because this is exactly the singularity I have. I just take this out, right? So then you can say, now, then we have actually 2 kappa I of R minus Ri plus sigma n equal 1 infinity An I R minus Ri. Let's call this equation 3. So this equation E R star, what about E 2 R star? E 2 R star equal R minus R A 1 over kappa I exponent 2 times sigma n equal 1 infinity and R minus R. Correct? You see now, this is a factor we want to get, right? We want to cancel with the Fi. So now, if we reduce V equal 1 over kappa I E kappa I T plus R star U equal minus 1 kappa I E minus kappa I T minus R star. We have UV equal minus R minus I kappa I squares exponent 2 kappa I sigma n equal 1 infinity and R minus I. Now you already see the pros why we do this. You see here? This is what we want, right? So if we divide by this one, then after the factor, the exact cancel this. This singularity disappear. This part is not singular, right? So this equation quite simple. Okay. Now we also want to see what's the D part. T square minus D R star square will equal D minus 2 kappa I R star D dV. Okay? This is exactly equal R minus RA exponent minus 2 kappa dV. See? It's exactly what we want, right? Very simple. So you first need to calculate some of the gravity chi. Then this is always the case. You see here T plus R star, T minus R star. Okay? This is actually the standard steps. ds squared equal F R d t square minus d r star square minus r square. This will be r minus r I g r. Then multiply here r minus r I y x 5. So I have finally together for remember when we write it, we were real simple. So this is not 0, this is not 0. So you can see this acre is perfect, okay, right? So we just simply get rid of this. So in this step, like what I said, I just assume this h equal 1 over r. So you can easily generalize this when this is not a whole. But the only thing, the singularity here has to be the same. Then there actually allow us to get this concept. The only difference is you just define a different GR, then expand. Right? Another trick, so I put F equal R minus R I GR. Why I put it in the denominator? Because I have 1 over F. So I expand this guy to get this one. Right? This actually just a mathematical trick. Because this actually, like I said, it's a simple singularity. So this is G R I different from 0. So this actually the same. So if you know this has been done, right? So then you just come back to what we just used, what we are, we, and I, we get the solution. I would like to write again. Everything already there, right? Then you just come to here. Okay. So this actually just give us rough ideas. What's the correspondence between TR in short chart case and the Kruskal extension? But I'm using Penrose's idea to show more concretely or more explicitly how the structure of the time, if this actually makes sense physically, right? This is pure mathematics. Is the analytic solution? Sometimes my title, I think in my notes, a Kruskal solution, because this is new solution. So beyond the cover actually such a solution. Or we can say a Kruskal extension. So this is a line for T positive. Okay, good. Any other questions? So I'm sure definitely you have lots of questions here. Not only you, including me. I think everybody has a problem. We are trying to understand, like what I said, even now, we still try to understand what's happening near the black hole horizon. We think, oh, black horizon, a lot of people, nothing. So you just one mirror brain. So really, it was nothing why we have to propose firewall or whatever. Just think something fits there, try to make our information loss come back. Right? Not so easy. No, so simple. Okay, so now we can consider this angle T positive. What about T negative? So you can see this angle is a line. This must mean this one. So I just related to draw it here. This, so again, start from here to here. So in the Slavichalak case, this, remember, it's not a real time. To look like the time, use T, but T meant specialized coordinates. So the trajectories, if it exists, starting from synchronoid and then pass here, the end this point. Okay? So this anchor is R equal constant surface, you see R equal constant, R becomes constant. So this anchor, time like capsule, space like capsule, time. T. So that's angle R, then when R equals 2m, and this angle exactly becomes 45. Right? So I can go to another side, this angle inside of a black hole, this is a white hole because we can see everything. If I'm sitting here, the light come out, I can see clearly what's on the inside. So that's why we call a white hole. But if I'm here, nothing comes out. My path is always go that direction, right? So this is a black hole. So, any question about this part? So this actually using this transformation by squeezing actually region 2 and 2 prime is the final region I get this picture, right? So once I get one impact, here we write this beautiful straight line. This is because we probably choose alpha, beta. If you have a different choice, you get some line here, then some people ask you, you can answer. That's fine, no problem. Just because you didn't probably choose, or you do not want to choose that alpha. Alpha equal beta equal square root of 2. You can choose a different constant. Okay? So now any questions? Now before we go to what's happening in regions of one. Yeah.
How do we visualize different infinities that we tell, like spatial infinity?
I'm going to do this.
Yeah.
Okay, good. Yeah. Well, I'm getting to actor because of region 2 actor represented. Yeah, good question. Okay, let's actually consider this case. Now in region 1 and 2. Regions 1 and 1 prime. We have x prime square minus t prime square equal r minus 2n e r over 2n t prime equal x prime hyperbolic t over 4n. So we just actually plug this actually this equation is 2, or this would be 3. So using our definitions actually we put v prime equal alpha tangential v bar and w prime equal alpha tangential w bar, where alpha equals square root of 2n, right? We already did. So this actually t prime equal 1/2, v prime w prime x prime equal 1/2, v prime minus w prime. So we use this actually, put it here, then we just get it the following. Times the v bar times w bar equal minus r minus 2 and then because of this you can see the whole plane, this angle will be v prime w prime is mapped to called diameter. Then you can see this actually is home map, but sometimes the singularities will cut the space here. This actually r equals 0, the cut another part. So that's why we get this Paris diagram. Okay? So you see it's simple. So now we just need to work out the details. So this is actually this map to the whole plane to actually this becomes half a pi, this actually minus half a pi, this pi, half a pi, this minus half. So this actually, now because the singularity our space-time has to stop here, then the rest has no physical connection with this part, I just simply throw it, right? The same thing for this part. Okay? So now we want to actually work out this details, how to get this. Now, in order to work out the details, now let's consider, for example, again, radius 2 and 2 prime. So I'm going to actually directly write out the relations. If you definitely do not need to remember, just go back to my notes. So you can see this actually the solution and the transformations between T and R and X prime. X prime equals T prime tangential T is 2 is 5. 5 now if I write this actually so because you see, remember our T prime equal 1/2 V prime plus W prime. So this actually our actual V term and W term is the same. So I just totally change this one to be consistent with my notes. So this actually X prime equal 1/2 V prime minus W prime. Then I can simply substitute here, right? So if I do this, then you can see. So this is T prime square minus X prime square for equal V prime W prime. Then V prime W alpha tangential. So I have this. This will give me alpha beta tangent V bar tangent W bar, right? So this actually equal, this actually equal to M minus R E R over 4 N. All I have actually, I take this R, all I have tangential V bar tangential W bar equal 1 over alpha beta 2 N minus R E R over 5. So this actually one equation we need, I put it here. Can you see? Sorry, this actually I wrote it very long. So we just want to write this in terms V bar and W bar. What's happening in Sushant, or more general, any kind of two-dimensional surface. This is mathematics. Physics is because it's a large count, I can give me a point, I can draw my large count. This is exactly 45 degrees, like what I did in Ghosh. See how simple it is. Then once I can draw my large count at each given point, I know time-like particle has to pass, has to inside this large count, right? So that's why yesterday when I draw the large count, I use no geodesics, although there are time-like, remember, there are no straight lines. But here is 45 degrees. The one cycle which is considered Pinkerton code is not a really 45 degrees. So that's why we use this one. Okay? Any question on this part? So first, mathematics, physics, and just the rest of the details, right? Like what we did actually. Just map everything out to consider R equal constant, T equal constant. They just give you the details. Okay?
Sir?
Yeah.
Sir, is it like a conformal mapping?
Sir?
Is it like a conformal mapping?
Okay, sorry about it.
Conformal mapping.
Yeah, this is conformal map. So like you see, I have a G, this let's say G, A, B, this omega squared G, A, B, right? But when I say conformal mapping, we just consider this part. Because this is not singular. Where we expand the space-time is this one. So this actually, Pan's diagram are only two-dimensional. You see? So we just actually, that's why we are in XR plane, because this is a plane we have phase. Zero phase is this S2, right? Yeah, good. This is exactly, but better to put this two-dimensional conformal. Then the causality in this space the same as this space. So no geodesics, not time-like, or not even space-like. Okay? So this actually is important. Another question? So when something complex, you just say, okay, let's see what's our goal? Why we do this? What's the everything behind the physics, right? Once we know the goal, why we do this, what's the physics, mathematics, the rest is just like what I said, fill in the details. Okay? So you can see, the idea is not really so complicated. It's simply actually mapping finite infinite region to a finite region. One example here. But actually, in Panel's diagram, instead of using that one, we use actually tangential mappings. Equals 0. Let's see, partial equals 0. This actually tells us if that equals 0, this is either equal 0 or equal actually pi, right? Or equal 1. So this actually t equal, this will be exactly this part. This actually, this is a line we brought equal minus down, right? So we brought because here, this is a line, for example, if I have we brought here, this actually, this guy has become negative, this is positive. So exactly, straight lines. So this actually t equals 0 case, then you want to say what's happening when I say t equal t1 greater than 0. Can you imagine where is this line? T is finite. Let's see here, the finite, right? This actually is minus. Right? Here is minus. So this actually minus. This is R equals 0. R equals 0. This is actually R equals infinity. R equals infinity. Infinity. This is R equals 0. You see now, this actually restrict my space-time into this part. Okay? This we already did this, I will not draw. This is R comes. Yeah. So we just get R equal infinity, R equal infinity, there are 4 solutions. So you can check it, right? So once I forget this, you can just simply fill in the R part. Any question about this part? It's simple, right? Not that difficult. This actually needed to be placed sooner like figure out all of that. So let's consider another one. Let's say R equal R. Now let's sure greater than 2n. This is positive. And this is positive. And then it's positive. Now the total is negative. So you can, I'll just simply draw this picture. This actually, there is a one line actually connecting this one. There's also R equal constant, R equal constant. This actually heavy surface R equal constant. Okay? So you see now, there's a point here. You can check for any given R, this will be a solution. Why, for example, this actual, there are actually 1 pi equal, 1 way pi equal half of pi, this is go to infinity, right? Infinity, but this actually equals 0. 0 multiplied infinity, there's a chance to give constant, right? So that makes sense. The same thing we're saying. Every actual line, some lines will give here, here. So you can figure out what's the corresponding line, the straight line from here to here. Because my alpha, beta are already fixed, right? So their corresponding to this guy's line, sure. No, this does not make much difference. So this actually graduate, this of course is 2n, this actually, let's say if it's 4m, then it's greater than 4m until R go to infinity. Okay? So this actually, you see, the R equal constant of surface in this diagram, right? Any question about this problem?
What is the interaction point of R equal to 0 and R equal to infinity?
R equals 0, remember where you read it?
This is I am
talking this one.
This one.
Yeah, there's actually, because the quadrant you can see here, this actually, how you can see, this R equals 0, they are not really connected physically. Because this map, you will see that point actually becomes single. But here actually, this is a partial point.
R equal to 0 is a point is singular.
Yeah, we have space singularity.
But these lines are interacting with the R equal to infinity.
This actually R equals 0, this R
This
infinity.
is R equal to 0.
Yeah, this is R equal constant. Okay.
Equal.
The whole task is point. Just because this particular map. Yeah. Okay. Sometimes misleading. So, but they are connected with this point. That's like a single point. Okay. And our good. So, yeah. So this actually is R equal constant case. The same you can go, let's see, consider what's happening with before we go there, let's say you can see R equal to m, I equal to m equals 0, right? I equal to m equals 0, which means either v equals 0 or w equals 0. Then this is exactly v equals 0. This line, w equals 0, this one. Right? This is actually the 25 degrees, the 45 degrees. This tells us that R equal to m is second, the like hypersurface, right? 45 degrees, remember? Always, this any point, if you give any point here, my large count is exact 45. So that's actually the advantage of time. Although the space-time is curved. Why? Because again, conformally flat. So conformally related to the constant. Right? So the cosine structure is the same in this point.
point that you're talking, that at any point if we draw the light cone, the angle is still 45 degrees. So
Yeah.
what you mean is that suppose we take any point on that diagram.
Let's see. Here?
So we take now the process of drawing the light cone is that we equate it to 0 and right. With that process of drawing the light cone,
You see here, if I consider this is my light cone, right?
Yes.
Under that point.
Exactly. So that light cone that you just drew means it is drawn in terms of the conformal metric or the old metric. That is what I'm asking.
The physical measure, right? So we have two. You have, let's say, ds squared equal gr dw bar dv bar minus r squared t squared, right?
Yeah.
But the program, like we said, this w equal constant, this is all v constant.
Yes.
So either in spatial space or Minkowski space. They are the same. Why? Because these two guys conform related by this conform factor G. So the light cone in this conformer space the same.
Yeah.
So that's why in Minkowski space is 45 degrees. Here is always 45.
The angle is preserved.
Yeah, I know.
Yes.
So that's exactly the advantage of panel diagram, right? Because they do not change the angle. But do not change the order measurement. They only for noise of this light. If you consider timeline, the work.
Okay. Can I say that suppose we take a point on that diagram inside any region in that diagram, and if we want to draw a light cone at that point, then we just need to draw lines that are parallel to that V bar and W bar axis, right?
Yeah, 45 degrees.
I'm clear.
Yeah.
That is what I wanted.
Oh, okay. This is exactly 45. It's like this one.
Yes. Exactly. That is what I wanted.
Like this one. Okay, good.
Thank you.
So this is a key 45. This is exactly this. Right. Good. Any other question? So you see that that's why panel diagram simple. If you really know how to draw it simple and directly give us the physical meaning. Okay? Not really physical meaning, unless directly give us the causal structure globally, you can see what's happening. Right? So like see, if I near what's happening here, then you have no way to choose. The only thing you continue to hit. And then you hit the same arc, right? The inside. So what's happening here? There's a chance for me to go up to here, right?
One more question.
Yeah.
Suppose here we are using a particular kind of transformation equation using the tan function, right? So suppose we use a different conformal transformation on the same metric. We start with the same metric. We use a different conformal transformation. So means the features of the diagram will be same, but maybe the shape will be changed, right?
Which one will be changed?
The features of the diagram, that is the singularities, the spatial infinities that we just do, they will be the same.
They will be the same. Maybe in ours, this is like one set of purpose, not a straight line.
So
this will be something like a curve, but the structure will be the same, physics structure.
yeah. So overall, what I'm asking is, has it been done that for the same metric, different conformal transformation has been applied and the Penrose diagram has been drawn?
Yeah, this cycle behind the Professor Pan, why we use his name, he proved all the actually conformally diagrams is equal.
Okay.
So because, for example, you see here, dx squared equals g d bar w bar minus r squared d squared. What you want to see what's happening if I use some different way,
Different
right?
transformation.
dv bar, let's go dw dv bar dv. I can use my dv, right? So this is actually my new d prime, right? Now I change to v. So I minus r square. So if you drop x prime equal 1 v prime minus w prime equal 1/2 alpha and get v bar minus beta and get w bar. This actually will equal 1 alpha tangent of v bar. Because I have a t prime, right? So plus beta tangent of w bar. Hyperbolic tangent t over 4m, right? So this x prime, this is actually my t. So if you simply look, this alpha, beta. So if alpha equal beta, we have the following. We have a tangent of v bar minus tangent w bar will equal tangent of v bar plus tangent w bar multiplied tangential t over 4n. You see now, I have two arbitrary functions. By writing this, I can cancel this alpha. This is actually I just choose alpha later, right? So then you can actually write this, or you can see this part will be. Then I will write this called sine v bar over cosine v bar minus sine w bar over cosine w. Then you just actually take cosine out. Finally, you will find this actual case. I'm going to write it down here. So this actual will give sine v bar minus w bar equal sine v bar plus w bar tangential t over 4. This is actually my second equation. See here? I have one, I have another one, tangential. Okay? So I'll just write now everything in terms of v bar, w bar, and the relation between alpha x. So there's another line I will copy it here so you can see clearly. Sine v bar minus w bar equal sine v bar plus w bar tangential t over 4m and another one tangential v bar tangential w bar equal. Now since alpha equal beta, I simply write alpha square. That will be 2m minus r into r4. So this actually erases 2 and 2 prime, right? So once we get this one, you can see now the rest actually, like what we did in the Karuska case, consider r equal constant and t equal constant, just to get some general idea, right? Now let's first consider the r equals 0. Why? Because I want to fix my alpha. So this actually, when r equals 0, you see, this is equal to n, this will be 1. So I have actually tangential wave bar, tangential W bar equal to n over r squared. Then you immediately see, if I choose my alpha equal 1, right? Then I get actually, here will be sine wave, sine W equal cosine wave, cosine W, right? Or I can take this another side, this will be cosine wave plus W equals 0. Equals 0, these two guys equals 0, either we get actually V bar plus W bar equal plus minus half pi. That's it. Now you see why I choose this alpha equal this one? Because then this becomes straight line, right? This is r equals 0. Okay, so now I want to say what's the straight line here? Rather, when you use the V W, the same. This angle is 0. That's why it becomes permanent. So this angle behind is the magnetic. Okay, yeah, good. Any other question?
So there is no light cone on the boundaries, right?
A light cone you can see, but you see if I put the light cone, but this is outside of space-time, right? But this light cone still for the body here, right? So this actually, but what's physically, you put that, this is always space-time. You cannot go there. So actually, if you send some bodies to this point, you will see you need an infinite time to reach the boundary, right?
And we will have event horizon in here?
I'm sorry?
Event horizon?
Okay, can you repeat?
Event horizon.
Oh, the horizon is here. Remember it's R2M. R equal to M is horizon. Right? So that's why you see here, for example, so R equal to 0, R equal to M here, R equal to M, this guy equals 0, right? This means V bar equals 0, or W bar equals 0. V bar equals 0, this is a V bar equals 0 case, right? W bar equals 0, this is W bar equals 0. So this actually exactly is horizon, because you want horizon. So that's why this actually, this is region to the inside of the black hole, this actually is region 1. This is the white hole, this is, we have another asymptotic region. Right? So they are outside of the white hole, also outside of black hole. This is two asymptotic regions. So physically, do we have this kind of structure? Normally we're thinking now, our universe does not have two asymptotic flat. Even our universe is not asymptotic flat, because the universe filled up with a matter, even in the infinite boundary, right? Our universe is homogeneous. Actually, any place looks the same. That's why our universe, in this case, if anything looks the same, and there's no boundary, there are only two geometry you can think. One is actually our ancestor belief, actually from India's philosophy. Remember, we have a big elephant. The balls actually, the universe closed, like spheres, no boundary, uniform, right? Another possibility is space-time goes infinity. You never get infinity. There are actually everything is homogeneous, the same. There's no boundary. Infinity means there's no boundary. There are two things there. Either I totally have a boundary like spheres, then every place is the same. Or my universe goes to infinity. No boundary, so every place you have the same density. You can imagine if I have a lake. If my lake has a boundary, the water actually near, in the boundary, of course, there's no water, right? how you can talk about the homogeneous case. If I have a sphere cover all the water, of course I can talk about the same density, right? Because this, my universe go to infinity. There's no boundary. There's nothing like a lake. The lake go to infinity. You do not have boundary. Because a lake and the water are always density the same. Even there's no boundary, so you cannot talk about where the near the lake is. Okay. So here, simply, this is like a boundary. Now, if we draw this finite, like we said, where R goes to infinity, we can mathematically always map to finite, right? So if you want to see really clear physics, you will see, I consider for example, time like that's no that's from here to infinity. You will see any point near here, from here to here, the time you need to take it infinity. So that's needed. Right? Okay, very good. Very good question. Yeah. Sometimes you say, okay, and the first, I'm okay. But when you come back, I get confused again. Right? Like what is, I think this is good like R equals 0. Any one R, or the R goes to infinity, why did you have the same point? It's difficult to understand. Not only for you to understand, it's difficult to understand. Everybody, how you can put it here, this is mathematical because of we use mathematical version or something similar. Okay, we put them. All you can see, this is some kind of project we have to pick when we draw a time star. Any other question? So this actually the R equal constant, now we can consider as a T equal constant case.
It will not be possible because tomorrow exam, I try, but we have to evaluate and then we have to make grade sheet, then it requires vice chancellor signature. So I don't think it will be possible. So we will post you. Every time I post the grade sheet. Grade sheet is official, it will give you 1 credit. Normally 3 credit course requires full 1 semester. But in this 5 days, you can take this as 1 credit, which will be useful for you. Shruti, why don't you sit in front? Right? So it will be 1 credit official by Government of India. That will be there. All right? So thank you.
Okay, thank you. So today we are going to continuously, this lecture will be lecture 7, Parallel diagram. This part, let me first write. Sometimes I call extension, sometimes I call solution, right? So the idea is actually the following. You see now, let's simply consider because this. I have dt squared minus dr squared minus r squared d omega squared, right? So I can introduce the uv coordinates, this will be 2 du or dw, let's see. Like what we did, and minus r squared t squared, right? So then you can say, okay, if I consider only in this like a TR plane, then the no geodesic, the no are either u equal constant or v equal constant, right? Now, actually, I need to radius. This actually means theta phi constant, this one. Then you can see the causalities here for example, is T, R. This actually is the light count, right? This actually, the light count. Correct? Now, you can imagine if I have, let's say, a Schwarzschild solution, I have actually this called, this is less, now I use G, R, D, W, D, V minus R squared, D squared. In this case, you see the same, sorry, this should be actually. You see now the no radial also W equal C0 with always equals the one, the constant. So the same, right? It's exactly because of this property. You see, even my space here, because here is actually Schwarzschild solution. This actually 45 degrees makes sense, even in curve space. What I want to see actually, even you see here, if I draw the diagram, here is O, here is P. This is still defined like count, right? Why this is the case? This is because if you look at this on this part and this part, they are conformally related, right? 1 week you already perfect. No, if you do not know, no problem. 1, 2 metric conformally related. The no geodesic still the same. This is exactly you can see either here. You see the no geodesic here is a V W equal constant, V tilde equal constant, the same thing here. So all of them 45 degrees, right? So the Panoram's diagram or even the critical extension, the important thing now, if I use double no coders, I can see directly my light cones on each point. They are exactly the same like in Schwarzschild case. Oh, because, for example, here, right? So now Panoram's actually had his first idea. He said, okay, yesterday we already saw the critical extends the whole space. Now he said, okay, in order to see clearly the totally global picture, I just want to map the whole plane to a finite region. Again, because of the no geodesic properties, so still 45 degrees. If you give me any given point, I can immediately tell you how the particles will actually move after that point, right? So that's actually a very good idea. We can say, okay, by looking simply at Panoram's diagram or this actually diagram, I can see the causalities. So that's actually the fundamental, the basic ideas. Okay? So this is the whole point to just map the whole point to find really there's infinity ways to map, right? I just like in my notes give one example. You can see, let's see, if I have a whole plane, this is 0 to infinity,